So traditionally, we would cover nomenclature, which is the process of naming your organic molecules. According to the IUPAC, International Union of Pure and Applied Chemistry, and a bunch of smaller subsections at the start of a bunch of chapters. Based on our kind of compressed environment, we're going to kind of just cover all the naming. In this class, I'm going to give you a general idea and capture of it. So at the start of chapter 3, we previously talked about the idea of how to name simple alkanes. And we kind of have this general setup where you have your locant, which is going to be the number. That would be number 1, 2, 3, 4, 5, 6, whatever. That's going to correspond to the location of something. We'll use locants to primarily describe substituents. Substituents are going to be anything else that is not connected to our main chain. Our main chain, or our parent, is going to be our longest continuous chain of carbons, which includes our key functional group, and our suffix is going to be a word to describe that functional group. When we're going through and trying to name a molecule, we'll kind of walk through these 3 fundamental steps. We'll start with identifying what is our parent group. Our parent group is going to be our longest continuous chain that's going to include our functional group. Now, most of the time, for simple alkanes, it's just going to be just a bunch of carbons. Where it gets a little bit more interesting, and we're going to talk about it in a second, is if you have different functional groups. For example, like a alcohol or a carboxylic acid or a ketone that you're going to include. Next, you're going to count your total numbers and give them your locants, 1, 2, 3, 4, 5, and then describe all of the substituents, everything else that you have on your molecule, and arrange those alphabetically by your substituent. Now, in terms of identifying or coming up with a number associated with your parent or your root, I have here a table showing all of the different numbering systems. The ones that we're going to primarily focus are in the 1 through 10. We have meth to describe 1, eth to describe 2, prop to describe 3, bute to describe 4, pent for 5, hex for 6, hept for 7, oct for 8, known for 9, and dec for 10. Now, our suffixes for alkanes are ane, so a 5-carbon system that is all single bonds we would describe as pentane. There are systems that can go up to higher. In the teens, what we'll do is we'll take the word dec and then add a thing before it. Unfortunately, rather than using the meth, eth, prop, bute, there is actually a new numbering system for 1 through 4, and everything else stays the same, which is super confusing. So 11 is undec, 12 is dodec, 13 is tridec, 14 is tetradec. Then you go back to your normal ones. You go pentadec, hexadec, heptadec. And here you'll notice you use the exact same root from above. So pent is 5. All you do is add an a. So it's pentadec, which is 5 and 10, which combine to 15. Nonadec is going to be 19, for example. Once you get up to 20, it's not decadec. Instead, it is icos. Once you go up to larger numbers, you use the word acant for your whole number or your integrals of 10. So 30 is triacant, tetracant, pentacant, so on and so forth. And you'll notice here that the 30 and 40 are going to use the 3 and 4 that is not your prop and bute. For the sake of our course, the 1 through 8 is really the ones that we're going to primarily focus on, but there's kind of a full capture of all of them. Now, for our functional groups, we've primarily focused just on having simple alkanes. However, you can have other types of functional groups. The 2 that we'll spend a little bit more time on are going to be the alkenes and the alkynes. Alkenes are going to be things that have double bonds, and alkynes are going to be things that have triple bonds. You can also have an alcohol, which is going to be an OH, an aldehyde, which is going to be a carbonyl that has a hydrogen, and then your carboxylic acid, which is going to have, this looks horrible, a carbonyl with like an alcohol on the side. So each of these are going to have a unique suffix, and that suffix is going to be something that's way at the end of the word. The alkane, alkene, alkyne are actually really nice because the ending, ane, ene, and ine are the exact suffixes that we are going to use. So if you have a 5-carbon system that has a double bond, we would describe that as a pentene, ene, rather than a pentane, which would be all single bond stuff. For alcohols, we use enol. So hexanol is going to be a 6-carbon system that has an alcohol. Now, if you just say hexanol, you really don't know where that alcohol is going to be because it can be on any of those 6 carbons. So a lot of times you will have a locant associated with where your functional group is. And that's going to be the case for your alkenes, alkynes, alcohols, aldehydes, carboxylic acids, if they're not all the way at the end or the beginning. Aldehydes and carboxylic acids are going to be something that we're going to talk a lot more in Organic 2, but here's just kind of a little bit of a preview of them. Now, we've also mentioned that there are going to be times where you have multiple of the exact same substituent. So you might have a 6-carbon backbone and you have multiple methyl groups off of it. Rather than writing, locant methyl, locant methyl, locant methyl, what we want to do is combine all of those like substituents and then use a prefix, di, tri, tetra, penta, hexa, 4, 2, 3, 4, 5, 6. Those are not used in alphabetical order. So if you have, for example, a dimethyl, the M in methyl is going to be what you're using to alphabetize them. If you have a penta-isopropyl, you ignore the penta and you're going to use the I in isopropyl for your alphabetical order. You can also have substituents that aren't just your simple alkanes, like a methyl or an ethyl, an isopropyl. Some of the most common are going to be your halogens. I guess I didn't include fluorine on here. Fluorine would be fluoro, chlorine is chloro, bromine is bromo, and iodide is iodo. You take the key part of the halogen and then add an O. You can also have nitro or amino groups, and those are other ones that won't take over as kind of like your main functional group, like we see with alkanes, alkenes, alkynes, alcohols. Now, after chapter 3, we also started talking about the idea of cyclic structures. We focus primarily on cyclohexanes, and as the name probably suggests, we're going to use a new prefix associated with this word, which is going to mean cyclo. The prefix, meaning coming before your parent root, is going to be a descriptor that all of those carbons are in a ring together. So if you have, for example, a cyclobutane, that means it's going to be a cyclic structure of 4 carbons for bute, and they're all going to be single bonded based on the ane. Similarly, cyclohexane are going to be 6-membered rings. Now, if you have a substituent off the group, and when we're drawing chair structures, we do this very often. If you have, for example, like a methyl group, if there is one and only one, you don't need to give it a location. So I have an example here at the bottom. That is a 5-membered ring. 5 has the word pent, so that's going to be a pentane, and because it's in a ring, we're going to call that a cyclopentane. Here we see that we have an ethyl group, which is 2 carbons that are going to be connected at a side chain. So we're just going to call this ethyl cyclopentane. There's no reason to give any numbering system for that because you'd give it a numbering of 1 and it's just kind of redundant. You can stick it anywhere and it's the same. When you start getting multiple substituents, then you do need to start using your numbers and your locants. So on that third structure there, we have a cyclobutane, which is going to correspond to the 4 carbons in the ring. There are a methyl group and there is an ethyl group. And when we have multiple substituents, what we're going to do is we're going to go in a direction, either clockwise or counterclockwise, and try to get the lowest possible numbers for our substituents. Kind of like when we were doing our normal locants and thinking, do we go left to right or right to left? So for example, if I call my ethyl group 1, I could either go 2, 3, and then 4, or 2, 3, and I can get either a 2 or a 4 for my methyl, and I'm going to go in the direction that's going to give me the lowest possible. So 1 ethyl, 2 methyl, cyclobutane. The one final thing is you can also have a cyclic structure as a root. So if you have a chain that's going to be longer than your cyclic structure, you can treat it the exact same and add just your YL. So you can have, for example, a cyclopropyl. So if you have a big long chain, which would just do, I don't know, squiggly lines, and then a triangle, so meth, eth, prop, we could call this a cyclopropyl, meaning it's a substituent, and use that as a individual component that is off your ring or off your main chain. So if you have a main chain that's a dodecyl, for example, and on one of the positions you have a cyclopropyl chain, maybe like the 4 position. So 4 cyclopropyl undecane, for example, could be a case where that happens. Finally, we've introduced this idea when we were talking about chairs and stuff. There are 2 extra words of cis and trans. Cis is meaning the same side. So you'll see you'll have 2 chlorines, where trans is going to mean the opposite. We have 1 low and 1 high. And these can describe things, especially about a double bond, where are they on the same side or opposite sides. In our very next video, we're going to bring in some stereochemistry, much like kind of R and S. We're going to introduce 2 new words, E and Z, and describe some stereochemistry about double bonds that isn't just cis and trans. So hopefully that kind of gives a little bit of a capture of all the different components about naming. In class, what we'll do is we'll have a big long list of different structures and we'll practice drawing them and naming them. So I'll go and see you in the next one.